this video I'll be reviewing the permutations and combinations unit. So for the most part, this unit was focused on finding the number of ways that a set of objects can be arranged. So anything from picking an outfit given a selection of pants, shirts, and shoes, total number of license plates you have given certain conditions, the number of ways you can draw prizes, the number of passwords that are possible given certain conditions. So we'll start with the fundamental counting principle, which tells us to multiply out the number of choices with each stage in our decision making. So this is probably at the base of everything that we do in this unit. If you can get the fundamental counting principle, then everything else follows from this concept. So you may find it helpful to list out, so if you have, for example, 3 decisions to make, list out 3 blanks, and you'll have to slot numbers into here. So for example, if you have 2 pairs of pants to choose from, 10 shirts, and 3 pairs of shoes, you multiply each of those decisions to find out the number of outfits that you can get from that. If you have a 3-digit number, you can list 3 blanks, and we'll require the first blank here not to be 0. So this can be anything from 1 to 9 here. And so there would be 9 decisions to make there. And then if you can repeat digits, this can be anything from 1 to 9, including 0. So there would be 10 possibilities for the second blank. And again, if you could repeat, this could be anything from 1 to 9, including 0. So 10 would be there. So this one would give you the number of ways that you can have a 3-digit number. So yeah, that's probably the biggest hint that I could give for fundamental counting principle. Start by listing the number of decisions that you need to make first, and then slide numbers in afterward after you analyze the data. So here's a question from one of the homework assignments. Computers code information in a binary sequence. You can have either a 0 or 1 for each term. And there's a sequence of 8 terms. It's called a byte. So you can have something like 00110010. How many bytes can be created? So if you have a sequence of 8 terms, 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 decisions to make. You can slide a 0 or a 1 in for each of those terms. You have 2 decisions to make for the first position. You have either a 0 or a 1 there. For the second position, you could have either a 0 or a 1 there, and same for the third, fourth, fifth, and so on. Then you multiply each of these together to get the total number of ways that you can make a byte. So this is 2 raised to the power of 8, or in other words, 2 raised to the power of 8 is 256. So we list out the number of decisions that we can make, and then slide in a number for the number of choices at each stage. Let's have a look at another example. How many license plates are possible if you have 4 letters, except for I and O, followed by 3 numbers with no repeats? First of all, you have 4 letters, and then it's followed by 3 numbers. So we require no repeats as well. So if we have 4 letters, I would write 4 blanks. I need to slide a letter into each one of these spots. And then we have 3 numbers that follow those 4 letters, so 3 go there. The number of letters in the alphabet, there are 26. We can't have I or O in there. So that's one condition. So 26 minus 2 gives 24. So there's 24 possible letters in play for these first 4 positions. But if we require no repeats, that means if I choose an A for this first position, I can't choose an A for any of these other positions. That's what they mean by no repeats. So we have a number of choices to make for the first position. We can pick anything from A to Z, excluding I or O. So we have 24 possible letters we can slide into the first spot. Now for the second spot, say we chose an A for the first spot. For the second spot, we could not choose A or I or O because this has been excluded from the options. So now we have only 23 choices left for the second spot. Now we've chosen two letters, say it was an A and then a B. The next spot, the third spot here, I can't have an A or a B or an I or an O. So 26 minus 4 will give me 22 choices left. And then once I've chosen that letter, I only have 21 left over for the fourth position. So for these three positions here, I have three numbers that are required. So if we can assume that we can have a 1 or a 0, anything from 0 to 9, 10 possibilities for this spot. So we can have 1 to 9 including 0, so that's where we get the 10 from. For the next position, we've already chosen a digit. For the first spot, say we chose an 8. For the next position, I could not have an 8 here, so there are only 9 choices left. Because we can't have a repeat, we can't have something like 8, 8. That would be not allowed. And then for the last position, we've chosen 2 digits already, so 2 out of 10 have already been picked. Now we have 8 left to choose. So finally, to get the total number of ways that we can pick a license plate, we multiply all these numbers together. We have all of these decision stages, we multiply them together. And once you do that, it turns out to be 183,617,208. So that is the number of license plates that we can have chosen with these conditions. Next thing we looked at in this unit was factorial notation. So factorial notation comes up quite a bit in our study of permutations and combinations. It's a shorthand way of writing a sequence of descending factors. So we might have something like 6 times 5 times 4 times 3 times 2 times 1. Instead of writing it out like this every time, we might have something like 5 factorial or 12 factorial. Rather than writing the whole product, we can just write it shorthand like this. We have a function in our calculator that can do this for us. We hit math, go to the left one, and then choose 4. If we wanted to find out what 4 factorial was, 4 times 3 times 2 times 1. So we could do it that way. It'll give us an answer. The other way we can do it is hit math, go to the left one, and go down and select 4. That gives us the same answer. So let's take a look at this example first. What is negative 4 factorial? It's important to note that we can't do the factorial of negative numbers, so this is impossible. Another example, 10 factorial divided by 7 factorial. Now when you're simplifying fractions, factorials in them, it's a good idea to expand the bigger term until you can see a cancellation. You can do this with your calculator, that's one way, but I'll just show you how to do it just on paper as well. You might find it a bit shorter. So expand the bigger term. 10 is the bigger one. You expand that one until you see a cancellation that we can do. So because the bottom has a 7 in it as well, 7 factorial, 10 factorial can be written like this. So we stop here because we can cancel 7 factorial with 7 factorial. So if you were to do 10 times 9 times 8, 10 times 9 times 8, that would give you this answer. If you were to do 10 factorial divided by 7 factorial instead, let's see what that gives us. There's 10 factorial divided by 7 factorial. Gives us the same answer. You might find it a bit quicker in some cases to expand the fraction first and then go from there. So another example, how many permutations of the word Yukon? There is 5 letters in the word Yukon, and if we're choosing all of the letters in which to work with, you can place any one of these 5 letters into the first spot. So for the first location, you can choose 5 letters. If you're assuming that you can't repeat any of these letters, so once it's chosen, you can't use it again, for the next position, there are only 4 letters to choose from, and the next there's only 3 because I picked 2 already, down to 1. So at the last spot, you only have 1 letter remaining which to choose from. So this will give you 5 factorial ways in which you can arrange the word Yukon. So 5 factorial gives us 120. 120. If the question asked you how many ways can you arrange 3 letters from the letters in the word Yukon, you would have 3 spots in which to put a selection of 5 letters. So you would have 5 choices for the first spot, 4 for the next, and 3 for the third spot. That would give you something else. So just something to keep in mind when you're reading these questions. I've got one more example that I'd like to go over for factorial notation. So here's the question. If we have this expression and we want to solve for n, look at this tip right here. Simplify fractions, expand the bigger term first. So we have a fraction here with factorials in it. We expand the bigger term. So the bigger term is n plus 1. So if we were to expand this, we have n plus 1. Factorial tells you to decrease by 1 each time. N minus 1, and then n minus 2. So I stop at n minus 2 because there is an n minus 2 in the denominator at this point. So n minus 2 is there. Well, so these n minus 2's will disappear. And then on the right side of the equation, we still have 20 times n minus 1. Let's just rewrite what we have here. We have n plus 1 times n minus 1. And then this equals 20 times n minus 1. So if we divide both sides by n minus 1, these terms will disappear. And then we have n squared plus n on the left side is 20. And then we can subtract 20 from both sides, which gives us this expression equals 0. So now we have a quadratic equation. We can factor this. So we need to find 2 things that multiply to give negative 20 and add to give 1. That turns out to be positive 5 and negative 4. Possible solutions for this factor equation are n equals minus 5 or n equals positive 4. If we were to substitute negative 5 back into this original equation, we can't do the factorial of negative numbers, so we have to exclude this solution. So our answer is 4 for this expression. N is 4.